Greetings! In this video, you'll learn why the Sony CXA1019 AM-FM radio chip is so great and appealed to listeners and radio home builders for over 2 decades. You'll learn about my history with the CXA1019 laden radio, and of course, we'll venture down the wideband FM signal path to gain some component-level insights about its form and function. You will also learn why we had to thrift store purchase 2 Sony clock radios to get an IC so that we could perform audio stage analysis and listening tests. In 1990, I camped for 5 nights with my brother in a forest. Immediately I noticed a white transistor radio hanging in a tree. It played an FM broadcast continuously for the duration of our camp. Spellbound, I asked to purchase this radio from my brother, and he gave it to me, no charge. Thanks, bro. Since 1990, this receiver, a Sony ICF350, has provided the backdrop for our gardening experiences. My Sony receiver contains the CXA1019S integrated circuit and operates with 2 AA batteries. The postfix letter S means that the chip is through-hole, but the IC package is smaller than a standard DIP footprint to conserve board space. We found at least 5 other variants of the CXA1019. These may have been precursors or perhaps were slightly altered to serve worldwide markets. We're unsure. Further, it seems that other manufacturers made these chips under license and they may have changed the part name. The CXA1019 provides monaural broadcast FM and AM and comes complete with an internal audio power amplifier. Sony did make incredible full stereo FM receiver chips without internal audio power amps, and I'll mention these again a little later. Further, Sony marketed the audio power amp contained in their AM-FM mono radio ICs as standalone audio power amp ICs. These included the CXA1019 and CXA1019. Sony intended the CXA1019 to function in 4 main areas: as a pocket portable standalone AM mono FM receiver, to go in cassette tape players, to go in clock radios, and as an AC powered standalone AM mono FM receiver. The CXA1019 serves as the anchor of a low parts count receive system where the IC is normally combined with a set of external passive components such as a main tuning capacitor, RF coils for filtering in the VFO, plus a ceramic resonator for use in the FM detector. This receive system is generally easy to align and stabilize. A key feature is low power consumption, something we'll show in detail in a few minutes. The CXA1019 continues to thrill builders and listeners alike. About 15 months ago, I became aware of the work of Technotrek via a short-form video. I later sought his YouTube channel and then landed on his GitHub repo, where he still maintains some tools to help you make a CXA1019S based receiver. The last time I ventured to Europe, friends were making CXA1019 or variant-based receivers from kits. Last year I found a kit online using an IC clone of the Sony CXA1019. Here's the datasheet for the CD1691CB from Wuxi in China. We'll view 2 more images and then go through the CXA1019 signal chain for FM radio. First up, battery life. Although we moved to rechargeables, For nearly 3 decades, my Sony receiver only needed a fresh pair of alkaline batteries for each gardening season. Assuming the 3-volt battery supply had a 2500 mAh capacity, my radio, when listened to moderate volume, drawing 10 milliamps, could last a purely theoretical 250 hours. Battery life alone makes the CXA1019 a fabulous chip for portable radios. Also, Sony uses a very sensitive and efficient speaker in my radio. Although the CXA1019 is an AM-FM chip, we'll focus on the broadcast FM signal path. We'll put some info about the medium wave AM parts and differences in our channel support blog. Our wee blog is linked in the description box. Antenna. From viewing datasheets, service manuals, and actual radios over time, a proper CXA1019 FM radio gets a telescopic antenna. For cassette players or clock radios, the antenna is often just a piece of wire in the plastic chassis, or perhaps even a long trace on the printed circuit board. Our next signal chain topic is the front-end bandpass filter. Recall that in a radio receiver, the front end is the circuitry between the antenna input up to and including the mixer stages. From our observations, there are 3 main scenarios used with the CXA1019. Number 1, skip the bandpass filter. Number 2, use a Sony factory part. For example, part FL1 as shown in this random Sony FM radio. As you may see, FL1 contains 4 pins. The third option is to make an input bandpass filter from an inductor etched into the printed circuit board along with fixed value capacitors to complete the filter. In Canada at least, the broadcast FM band goes from 88 to 108 MHz, a 20 MHz bandwidth. Not including an input bandpass filter means a whole ton of signals are getting boosted by the RF amp and entering the mixer RF port. Perhaps for a clock radio, this is a price point compromise you may take. Proper FM radios normally include some form of a bandpass filter to attenuate image and strong out-of-band signals. Before we move on, the main radio tuning cap in a CXA1019 based radio usually contains 4 ganged together polyester film dielectric variable capacitors. 2 ganged variable capacitor sections are dedicated to the AM radio, while the other 2 ganged sections serve the FM radio. Following the input bandpass filter, we'll now discuss the RF amp and tracking bandpass filter. The RF amp requires little fanfare. It runs low current, so intermodulation distortion is not a pressing goal. The front-end power gain is 30 to 35 dB with an active mixer, so likely the RF amp provides in the order of 15 to 20 dB power gain. The single-tuned output inductor capacitor tank of the RF amp gets tuned by one section of the main tuning capacitor. The other ganged main tuning capacitor section simultaneously tunes the VFO. Thus, the RF amp's output bandpass filter tracks the VFO. Let's examine a vintage, modest-grade FM tuner from Mitsubishi. This receiver employs a quadruple ganged main tuning air variable capacitor. Gang number 1 tunes the single tune input bandpass filter just before the dual gate MOSFET RF amplifier. Gangs 2 and 3 tune the double tune bandpass filter that follows the RF amp. The 4th gang tunes the VFO. Whether using ganged variable capacitors or varactor diodes, filter plus VFO tracking is how many narrow and wideband FM amplifiers provide front-end selectivity over wide input receiver bandwidths. Let's examine what filter tracking across both ends of the broadcast FM band looks like with the tracking generator plus a spectrum analyzer. In 2012 to 2015, I became obsessed with VHF, UHF, and FM reception. I built this filter using a triple gang capacitor, although only 2 sections get used. Each capacitor is series connected to an air-wound inductor, and the 2 tanks are coupled with a piece of green enamel-coated wire. Here lies the transfer function at the high end of the band. I was mostly looking at minimizing filter losses. As shown, the filter loss is around 2 dB. At the low end of the FM band, sadly, my losses were around 6 dB. However, you can see that we may peak this bandpass filter across the 20 MHz bandwidth of the broadcast FM band. We've already mentioned the mixer. It's probably an emitter-coupled pair and offers gain at the output intermediate frequency of 10.7 MHz. In many FM receivers, mixers are simple and unbalanced. We'll focus on the ceramic resonator, the IF filter. For my clock radio, I determined that the 3D bandwidth of the ceramic filter was 280 kHz, about as wide as a barn door. Broadcast FM radio is channelized, except at the band edges the adjacent station, up or down, is around 200 kHz away from the center frequency of the currently tuned station. With a single 280 kHz IF filter, worst case, adjacent channel rejection is only around 10 dB. This clearly shows why a CXA1019 based receiver is not a DX machine. If I tried to tune a weak DX station on a clear channel, the adjacent channel local station, or perhaps its image, would drown out my desired DX station. We'll now cover the limiter and detector, which concludes this section. In Part 3, we'll dive deeply into the amazing audio stage found on the CXA1019 and then wrap up. You're viewing the schematic of the TA7061 Alpha Papa, a venerable IF-amp limiter that easily shows how most IC IF-amp plus limiters function. The schematic shows some biasing circuitry plus 3 emitter-coupled pairs, numbers 1, 2, and 3. An emitter follower follows stage 1 and 2 for level shifting. The IF signal is amplified in numbers 1 and 2 and ultimately overdrives the number 3 emitter-coupled pair. This clips off amplitude variations in the signal and gives a square wave output with a 50% duty cycle, much like a flip-flop in digital ICs. We only want frequency variations, no AM or impulse noise. The output signal level stays constant even when the input signal varies. An amplitude-limited, constant amplitude IF signal ultimately boosts the fidelity of the demodulated audio. Before tackling demodulation, let's show our reference paper, the 1967 Pinnacle paper by Bellotti and Pepper that presents the world's first quadrature detector on a linear IC. This was a game-changing paper for both FM radio and TV worlds. 2 essential terms are phase detector and phase quadrature. A phase detector is a frequency mixer, analog multiplier, or logic circuit, usually a NAND gate, that generates an output signal which reflects the phase difference between 2 input signals. 2 signals are considered to be in phase quadrature when their phase difference is exactly 90 degrees. A quadrature FM detector demodulates an FM signal by splitting the incoming signal into 2 paths, shown here as X and Y paths. Path X gets the limiter's square wave output with 0 phase shift. Path Y passes through a frequency-dependent phase shifter, which is an external 10.7 MHz ceramic resonator attached to the CXA1019. This resonator provides a quadrature or 90-degree phase shift at exactly the IF center frequency of 10.7 MHz. As the carrier deviates from the 10.7 MHz center frequency from modulation, the Y-path phase shift will pass below and above 90 degrees dependent upon the direction of deviation. A phase detector ultimately detects and translates the phase difference between X and Y into recovered audio in the CXA1019. Here lies Bilotti and Pepper's schematic. Note the 3-stage limiter we discussed previously. The phase detector is fully balanced for high performance. The 2 emitter-coupled pairs are cross-coupled, similar to the top switch quad in a Gilbert cell multiplier. The bipolar transistor phase detector here and in the CXA1019 function as an analog multiplier. Analog multipliers produce an output signal proportional to the product of its 2 analog inputs. Section 3, the CXA1019 audio stage. For $6 we got this clock radio containing a CXA1019 at the local thrift store.
Is a little known and relatively new class of diseases called autoimmune
in the original space with the full rebuild.
Except
Perfection is hard to find, except maybe when you...
Construire une nouvelle fusée, il a exigé que cette expertise et surtout ses
After extracting the CXA1019S, we attempted to audio test it, but instead got oscillations, or to be exact, modulated HF oscillations. Before we could solve this, we accidentally shorted and then blew up our 5-volt Zener diode regulator, thus exposing the chip to around 11.6 DC volts. Boom. Yep, it fried. So then back to the car to return to the thrift store with hope and glee we might find another clock radio. Happily, they had another in stock, this time a white-colored model. All good. Having secured and extracted a fresh CXA1019S, we flipped the chip upside down, dead bug fashion, in order to audio test it. Essentially, we had to bypass every non-audio pin to ground with an appropriate RF or AF capacitor. With joy and relief, no parasitic oscillations were measured. Happy days! We placed a nearly indestructible and equally husky L7805 voltage regulator to avoid further chip destruction from stupid mistakes with clumsy hands. At first, we tested the active audio volume control circuit with a 50K pot per the data sheet, but eventually used fixed value resistors to set pin 5's DC voltage to 0.5 volts, which gave a voltage gain through the chip of about 6.2. We then measured the entire chip's quiescent current in FM and then AM mode. The actual audio stage quiescent current is around 3 milliamps, amazingly low. Kudos to the Sony design team that engineered and fabbed this IC. Here's a couple of photos of our breadboard. Before we view some DSO time and frequency domain screen captures of the audio stage, let's briefly discuss the audio finals in the CXA1019. Recall that a typical CXA1019 based radio usually runs on battery voltage supplies between 3 to 4.5 volts maximum. By the time the gardening season is beyond half over, our batteries may be down to 1 to 1.2 volts each. However, the radio keeps working. As shown to the left of your screen, a typical complementary emitter-follower output pair syncing and sourcing the speaker load just won't cut it at low DC voltage. With true Class A-B biasing, you might get a maximum or sinusoidal output of 2.25 to 2.5 volts peak to peak if you were to breadboard a discrete power amp. From its datasheet, the CXA1019 uses what is termed rail-to-rail output finals. The load, a speaker, connects to the collectors rather than the emitters of the push-pull transistor pair. This allows the AC output voltage to run closer to the 0 and 5 volt DC rails. In the lab, we drove the 5 volt powered CXA1019's audio input with a 1 kHz signal. The output is AC coupled to a 7.6 ohm resistor. We connected our DSO probe across the resistor load output. Let's view some screen captured outputs of our DSO with its high quality maths FFT algorithm. This slide shows the AF amp output in time domain when driven to 2 volts peak to peak. This sine wave looks clean. Let's move to frequency domain. Overall, the harmonic distortion is low except for one tone, the third harmonic. Now we'll increase the drive to 3 volts peak to peak. The sine wave looks okay. Move to frequency domain. Overall, the distortion for the second, fourth, and fifth harmonic are a bit lower than when driven to 2 volts peak to peak. This is actually a normal observance for rail-to-rail output finals. But again, the third harmonic stands out. What about 3.5 volts peak to peak? Sine wave still looks good, but in frequency domain, all harmonic tones rose a few dB higher. Let's go to 4 volts peak to peak. Uh-oh, the sine wave shows some distress. In frequency domain, harmonic distortion is really taking off. Time domain at 4.25 volts peak to peak. We are heavily clipping. Some conclusions. In this CXA1019S, until we get somewhere between 3.5 and 4 volts peak to peak, only the third harmonic gives us grief. I believe this is from the intentional low bias of the power finals, and probably reflects crossover distortion. Because only the third harmonic tone is strong, the total harmonic distortion is still low, and we don't really hear the offending third harmonic at normal listening volumes. Let's have a listen. This audio is right off the camera, unedited. What can I say? At moderately loud listening volumes, this amp only draws 10 milliamps. We hope this video showed the greatness of the CXA1019, plus gave some useful insight.